In this video, we'll be discussing logarithmic and exponential equations, which comes from section 6.6. If you recall, back in section 6.4, 2 videos ago, we were solving logarithmic equations by changing exponential form. So we were changing from logarithmic to exponential form. We can do that here. So let's recall how we did that in those videos. Here we have a log function, log base 5 of the argument, which is inside the parentheses, equals 2. Recall, the domain of any log function says that everything inside these parentheses has to be greater than 0. You cannot have 0 inside these parentheses. You cannot have a negative inside of here. So whatever this value is, it has to be greater than 0. Now, in order to solve this, let's put this in exponential form. Recall, an exponential form, the base 5 to the power of 2 is equal to the argument. So 5 to the power of 2 is equal to the argument. This is easily solvable because this is a quadratic. To solve quadratics, we set it equal to 0. So this becomes x squared plus x, and then we're going to take this 25 and subtract it from both sides. So this becomes 13 minus 25. To solve quadratics, we factor to solve. Two numbers that multiply to make negative 12 but add up to 1 would be x plus 4 and x minus 3. Using the zero product property, this tells us that the answers to x are going to be negative 4 and 3. But before I decide that those are in fact the two answers, we have to check for an extraneous solution, or possibly a solution that does not fit the domain. We need the argument to be greater than 0. So let's first check negative 4. If we plug negative 4 into the argument, we have negative 4 squared, which is 16, minus 4, which is 12, plus 13 makes 25. So if I plug negative 4 into my argument, I indeed get a positive number. So that is okay because my argument must be greater than 0. So negative 4 is indeed a solution since it checks out inside my domain. Let's also check the answer 3. 3 squared is 9, plus 3 is 12, plus 13 is 25. Since this is a positive number, it also meets the domain, so that is also a solution. So both of these answers are part of my solution set. Let's also change this to exponential form to determine whether it also is to solve for x. So let's put this in exponential form. Recall what the base of a natural logarithm is. The base of a natural log is e. So there is a hidden base in here, which is a base of e. So when we change this to exponential form, this says e to the 8th power equals the argument. The argument is this inside the parentheses, which is e to the negative 2x power. Now by solving, we have two bases that are equal to each other, which means that their exponents must be equal. So this means x is negative 4. But before I decide that this is the only solution, we have to make sure it makes my argument greater than 0. So let's check negative 4 inside the argument, which is inside those green parentheses. E to the negative 2 times negative 4, well, negative 2 times negative 4 is 8. So e to the 8th power is a positive number. So that means the argument is greater than 0, and this number does check out. So this would be the only solution. Now let's recall a couple of characteristics that we know about logs that we learned in previous videos. We just used this rule up here that says if the bases are equal, then that means their exponents are equal. Also, we know that if logs are equal and having the same base, then that means their arguments are equal. And then we can go the other direction also. If the arguments are equal, then their logs are equal. So what this one is saying is really going to be pretty useful. In order to solve for something that's equal to each other like this, you could take the log of both sides. So if I have m equals n, I can put a log in front of the m, a log in front of the n, and I could say that they are still equal to each other. Just like balancing an equation. If whatever you do to one side, do to the other. So if I take a log of the left side, make sure you take a log of the right side. And that's going to help us in solving some of the future equations. For example, sometimes we have to manipulate these equations and use properties of the logarithms in order to solve. But always check for extraneous solutions. Since logarithms of negatives are undefined, we will always have to check for extraneous solutions. So let's solve this logarithmic equation. In order to solve, the easiest thing to do is to get a log equal to a log, but there cannot be a coefficient in front. So if there's a coefficient in front, we want to get rid of that by moving it to the exponential area. Remember, anytime there's a log, that coefficient can also be written as an exponent of the argument. So if I were to rewrite this, I would rewrite this as log base 3 of 4 equals log base 3 of x squared. Now using this rule here, if you have the same log with the same base on both sides, you can set their arguments equal to each other. So since I have log base 3 here and log base 3 here, we can simply just say that their arguments 4 equals x squared. Now if I take the square root of both sides, I find that x equals plus or minus 2. Now again, before I decide that that is the only two solutions, we must check for extraneous solutions first. So let's put 2 in for x. Well, x is the only thing in the argument field. So when I put 2 in for x, that makes my argument positive, so 2 checks out. However, when I put negative 2 in for the x, which is the argument, I get negative 2 for the argument, which is a negative number, and we cannot have negatives in the argument field. So negative 2 actually is not a solution. The only number that checks out is 2. Negative 2 is extraneous. Let's try this next one. Here we've got log base 2 of x plus 2 plus log base 2 of 1 minus x equals 1. When we have two separate logs with the same base, we should combine them together to make one single log. In order to create one single log, they have to have the same base. And when those two logs are added together, we multiply their arguments. So this becomes x plus 2 times 1 minus x. So I've combined this into one single log. So now what I'm going to do is I am going to FOIL this out. So this becomes log base 2 of x minus x squared plus 2 minus 2x equals 1. And then I'll put this in exponential form. Exponential form says the base 2 to the power of 1 equals this argument. So if I'm going to write this argument, I have negative x squared. I'm going to combine x and negative 2x to make negative x here. And then, since we have a quadratic, I'm going to put everything together. I'm going to move these three terms over to the left side because I don't like that the first term happens to be negative. So I'm going to move all of these terms over to the left. So I'm going to add x squared. I'm going to add x. I'm going to subtract 2, and when I subtract 2, I have 2 minus 2, which is 0. So now that I have a quadratic, I can factor. Since there is no third term, I simply can take the greatest common factor out of these first two. So I'll take the x out, and using the zero product property, this tells me that x could either be 0 or -1. But of course we should check for extraneous solutions. Let's start with 0. If I put 0 into this argument, I have 0 plus 2, which is positive, so that checks out. But we also have to make sure that it makes this positive as well. 1 minus 0 is also a positive number, so 0 does check, since both arguments are greater than 0. So now let's check -1. -1 plus 2 is 1, so this is positive, so that checks out. 1 minus -1 is actually 1 plus 1, so that's 2, which is a positive number, so that also checks out. So both of these answers are actual solutions. There are no extraneous solutions. Try another. We have natural log of x plus natural log of x plus 2 equals 4. So first thing we're going to do is we're going to combine logs. Both of these logs have a base of e since they're natural logs. We're going to combine them together in one single natural log. Since they're added together, we're going to multiply their arguments. Next thing I'm going to do is I'm going to put this in exponential form. Well, we know that the base is e since it's a natural log, so we're going to take e to the 4th power equals the argument. I'll go ahead and distribute that. So that's x squared plus 2x. This is quadratic. We always want to set quadratics equal to 0. So this becomes x squared plus 2x. And then I'm going to subtract. This is a constant. E is 2.7 run on decimal. It's a number raised to the 4th power, so this is a constant, not a variable. So I can subtract this to the other side, and this is our constant, which is in the 3rd position of this trinomial. I would have no clue how to factor this, so we're going to use the quadratic formula to find out what x actually is. So to find x, we're going to put these coefficients, 1, 2, and e to the 4th power in for a, b, and c. So quadratic formula says x equals -b plus or minus the square root of b squared minus 4 times a times c all over 2a. So when I simplify this, I get -2 plus or minus the square root of 4 plus 4e to the 4th over 2. And when I put this into my calculator, everything underneath this radical I'm going to do in my calculator here. So I have just underneath the radical is 4 plus 4 times e to the 4th power. And that gives me approximately 222. So I'll just get an approximation for this answer. So this becomes -2 plus or minus the square root of 222.39 over 2. So that means x is approximately, when I put all of this into my calculator, I'm going to have -2 plus square root of 222 all that divided by 2, which gives me one answer at 6.456. And then I'll have another answer when I put that subtraction sign in there. So let's put the subtraction sign in. So I'll do the exact same answer I had before, but this time I'll put a subtraction sign in there. So then I get another answer at negative 8.456. But don't forget, we need to check both answers. So let's go back up to the problem, and we need to make sure that both of these numbers leave positive arguments. The first argument is x. When I plug in 6.456 into this argument, it's positive. When I plug 6.456 into this argument, it's also positive. So this solution checks out. However, when I plug in negative 8.456 in for this argument, it's negative. It's also negative in this one. But even if it just makes one argument negative, then it is not a solution. That means it is extraneous. So I only have one possible solution for x in this problem, which is approximately 6.456. Let's talk about some details of logarithmic and exponential equations. So on this side, we're supposing we want to solve for 3 to the x power equals 7. I always ask my students to first estimate what they think this answer is going to be. This is a fairly simple one to estimate. I know 3 to the first power is 3, and I also know 3 to the second power is 9. So when I ask 3 to the what power is 7, clearly x is going to be a number that is somewhere between 1 to 2, because we want the answer, or the argument, to be somewhere between 3 and 9, since the answer is 7. So I know this exponent is going to have to be 1 point something. So to know about where your estimate is going to be will help us in determining the answer, making sure we don't get any silly answers. There are two ways I'm going to do this particular problem. The first way you could do this, this would be option 1. Option 1 is to write it as the exponential equation as a logarithmic function. So if I were to write this as a logarithmic function, 3 is the base, 7 is the argument, and the exponent is x. So we're basically trying to solve for this exponent x, which actually is equal to everything inside of here. However, our calculators, most scientific calculators, cannot put this into their calculator because we only have common logs, which is a base of 10, or a natural log, which is a base of e. So in order to calculate what this is, we have to change the base. In order to change the base, this becomes log of whatever base you pick. I'll pick base 10 since my calculator has that, of the argument divided by log base 10 of the base, and that also will equal x. So if I put this into my calculator, that will be the same as the orange rectangle that I have above, and I can actually calculate that second one. So if I calculate that, I have log of base 7 divided by log of argument 3, and you get approximately 1.77, which is exactly what we thought it was going to be, somewhere between 1 and 2. We obviously can check this. We would take this number and plug it in as our exponent x. So I'm going to do 3 to this power, I should get 7. So 3 to the power of, I'm actually going to bring up my previous answer, so that way I don't have to type in just 1.77 and round it. I'm going to do 3 to the previous answer, so that way it's 1.77 and all of those decimals will be already memorized in its memory. And I get 7. Let's try that one more time with another problem. Here we have 5 times 2 to the x power equals 3. It's very similar to this last question, except for it's got this 5 out in front. Now you can't change this into logarithmic form just yet because of that coefficient. So the first thing I need to do is I need to get rid of that coefficient out in front. By doing that, I then have 2 to the x power equals 3/5. And if at this point you want to change that to 0.6 because you're more comfortable with decimals, you can do that because 0.6 is an exact value. And now this looks exactly like what we started with before, and we can put this into logarithmic form. Logarithmic form says log base 2 of 3/5 equals x. So if I could solve this, I can find the exponent that will make this come true. Well, in order to do that, we need to put this into change of base form. So this becomes log of 3/5 divided by log of 2, and that will equal x. Let's find an approximation for that number. So log of 3/5 divided by log of 2, and we get the answer is negative 0.7369. I'll just round it to 737. And obviously we can indeed check this answer. If we use that number as the exponent over here, I can do 5 times 2 to this power, and I should get 3. So let's try it. 5 times 2 to the power of the previous answer gives me 3. Now, there's a second option, okay? This is the second option to solving that same problem that we did up above, up here, okay? We already know the answer is 1.77 to this question. 3 to the 1.7 power is 7. Another way we can do this, the second option, you might prefer this option instead, is to take the log of both sides. Rather than turn this whole thing into logarithmic form, we can take the log of both sides because that's an algebraic step that we can take. So I'm going to take the common log of the left side and take the common log of the right side. Make sure the bases match. Otherwise, you're not doing the same thing and your equation then becomes unbalanced. Now we use properties of logarithms to solve this. Since I have log in front of this argument that has an exponent, we can pull that exponent down in front. So this becomes x log 3 equals log 7. And to solve for x, I can divide both sides by log 3. So this means x equals log 7 divided by log 3. And when you put that in your calculator, you get 1.77, which is the exact same answer that we had up here. But after we changed the base, we had log 7 divided by log 3, which is exactly what we have here, and we get the same answer. So you can see that option 1 and option 2 will result in the same answer. So let's try option 2 and do this a couple more times. Here we have part B. We're going to take the log of both sides. So log base 2 to the x minus 1 equals log base 5 to the 2x plus 3. Because we put those logs in front, we can take the exponents down in front of the logs. So this becomes x minus 1 times log of 2 equals 2x plus 3 times log of 5. Now we need to solve for x. So what I'm going to do is I'm going to distribute so I can get those x's out of those parentheses. So this becomes x times log 2 minus 1 times log 2 equals 2x times log 5 plus 3 times log 5. Now the goal is to get these x's together on one side of the equation. So I'm going to move these two terms over to the left side, and then I'm going to put these two terms without the x over to the right side. So let's start by subtracting this term and moving it over. So x log 2 minus 2x log 5. And now I'm going to take the log 2 and I'm going to add it and move it over here. 3 log 5 plus log 2. Now that we have the x's on one side of the equation, I'm going to factor it out in front. So x times log 2 minus 2 log 5 equals 3 log 5 plus log 2. Now that the x is isolated, all I have to do is divide by the factor that's multiplied to it to the other side, and I'll have x all by itself. So let's divide both sides by log 2 minus 2 log 5. So I have x equals 3 log 5 plus log 2 over log 2 minus 2 log 5. This is the exact answer of x that will make this come true. Let's find the approximate answer by putting this into our calculator. In the numerator, we have 3 log 5 plus log 2. In the denominator, we have log 2 minus 2 log 5. And our approximation is negative 2.186. That number we can use to check to see whether this is a correct statement. So on the left side, we'll do 2 to this power. On the right side, we'll do 5 to this power. And if those two sides equal, then we know we've checked it. So let's go ahead and do the check. So on the left side, I'll have 2 to the power of negative 2.186 minus 1. So on the left side, we'll have negative 6.372. That should equal the right side, which is 5 to the power of negative 2.186 times 2 plus 3. Oh, I did something wrong there. Let's try the right side again. Maybe I did something wrong on the left side. Let's try the right side. This is 5 to the power of 2 times negative 2.186 plus 3. Okay, so this on the right side I got 0.1099. Let me check the left side. Maybe I did something wrong. If I get the same answer again and these aren't equal, that means this answer wasn't correct. So let's check one more time. Left side, 2 to the power of negative 2.186 minus 1. Oh, I must have done something wrong in the first calculation. So since the left side and the right side do indeed equal each other in this equation up here, that means this is the solution. This would be the exact solution. This would be the approximate solution. All right, let's try 2 more problems. Do it the same way we did the last few. We're going to take the log of both sides. And it doesn't matter if you take the common log or the natural log. So for example, if I wanted to solve this with a natural log, I could. I could do natural log of 5 to the 4x plus 2 equals natural log of 8. So when I take that exponent down in front, this becomes 4x plus 2 natural log 5 equals natural log 8. So then I'm going to distribute. I have 4x natural log 5 plus 2 natural log 5 equals natural log 8. By isolating this x, I'm going to subtract this term to the other side. So I have 4x natural log 5 equals natural log 8 minus 2 natural log 5. Then my last step, what I'm going to do is I'm going to divide everything by 4 natural log 5. So that means x equals natural log 8 minus 2 natural log 5 divided by 4 natural log 5. So this is the exact answer. Let's find an approximate. Natural log 8 minus 2 natural log 5 divided by 4 natural log 5. And we get an approximate answer of negative 1.177. And of course, you should always check your answers. Let's try one more. First, in order to take logable sides, you must get rid of any coefficients that are in front of the base. You cannot multiply these numbers together because this number does not have the same exponent as this one. So you cannot multiply these together. So the only way I can get rid of the 25 is to divide it out. So that's going to give me 20 equals 1.1 to the 3x power. So now I'm going to take logable sides, or natural log, whichever you prefer. I can bring that 3x as an exponent down in front of the log. So this becomes natural log 20 equals 3x times natural log 1.1. Then I'll divide by 3 natural log 1.1. So I have x equals natural log 20 over 3 natural log 1.1, which is approximately 10.477. And of course, you would check that answer.